This is the arachidonic acid cascade. It's a map of the metabolites of arachidonic acid. It shows the biosynthetic pathway to, amongst other things, the prostaglandins. These metabolites together are an important class of compound in the body. They mediate a large number of physiological functions. The same precursor is ultimately the root of all these compounds. It's arachidonic acid, which is one of the body's essential fatty acids, from which the whole cascade takes its name. One branch leads via a single intermediate to a group of compounds called the leukotrienes. These are involved in the process of inflammation and allergy, and are therefore potentially very important medically. An alternative branch leads to another group, the prostaglandins, which are dealt with in the case study. Prostaglandin H is a precursor of prostaglandin D2, which inhibits blood platelet aggregation and acts as a vasodilator. This group is very important in the body. One part of the same branch is prostaglandin E, which controls smooth muscle contraction and has been used to induce labour. From the same precursor, which gives rise to the prostaglandins, two other pharmacological important groups arrive. These are the thromboxanes and prostacyclin, which together have important functions in the cardiovascular system. Interestingly, they have totally opposed effects, and the balance between these two is thought to maintain a healthy vascular system. Clearly, these vital compounds provide a starting point for designing drugs to correct imbalances in the body. But there's a problem. They are autocoids. That is, they are produced very close to their site of action and tend to be very short-lived. Thromboxane A2, for example, has a half-life of 30 seconds and is very rapidly chemically degraded to an inactive metabolite. Because they're autocoids, they're not selective in their operation. PGE2, as well as inducing labour, causes nausea and vomiting because it also binds with receptors in the gastrointestinal system. So, if you want to make a selective medicine, you need to target a single receptor. This means we need to focus on synthesizing analogues, which are selective, reasonably stable in the body, and don't have side effects. But what strategy do you adopt for such drug design?
Well, clearly, if you want a selective medicine, you have to be able to differentiate between the various sorts of prostaglandin receptors. As you've seen, prostaglandin E has a variety of different activities, and if we want selective drugs, the name must act at just one of the receptors rather than all of them. So the first question you have to ask is, how many receptors are there? Because, of course, you may not be able to make a selective medicine. Now, in order to try and discover how many receptors there are in the body, we make close analogues of the natural product and test them on various tissues, hoping that we may differentiate activities on the various tissues by changing slightly and subtly the structure of the drug. Now, whilst we were actually in the process of doing this, we made ANH 19437. Now, as you'll see, this compound is actually an analogue of prostaglandin D2. Although, as it turns out, when we tested the compound, it had no activity whatsoever at prostaglandin D2 receptors. But it did turn out to be, and this was very surprising, a selective thromboxane antagonist. Now, this was exciting because it was, first of all, the world's #1 thromboxane antagonist. Nobody had ever observed such an activity before. But also, we had good evidence that thromboxane A2 was in some way responsible for the formation of platelet thrombi, and also was a very potent vasoconstricting agent. And it had been suggested that it was involved in the disease process that eventually leads to stroke and heart attack. Now, clearly, if we could actually antagonize these effects, then we might have a very important medicine.
Now, this may sound straightforward, but a research program like this entails a great deal of chemical problem solving. Central to this is devising a flexible synthetic pathway that can easily be modified to lead to a range of prostaglandin analogues, such as our candidate compound, the thromboxane antagonist. We must also be able to control the stereochemistry, since the configuration of of up to 4 chiral centres needs to be defined. Let's now look at how this was achieved. One of the key features of the prostaglandins and their analogues is the fact they contain a 5-membered ring. It therefore seems logical to begin the synthesis with this component already formed.
Well, our starting point is cyclopentadiene, because it's a cheap, cheerful, readily available chemical, which is obviously important when we're talking about an industrial synthesis. The first stage process is going to be to functionalize one of the double bonds by use of a cycloaddition reaction with dichloroketene. And this then gives us this bicyclic dichloroketone. The 2 chlorine atoms will be removed via a zinc and acetic acid reduction. And this then gives us a bicyclic ketone, which is going to be the common starting point for a vast amount of prostaglandin chemistry. Now, clearly one of the problems in making a prostaglandin is that you have 4 asymmetric centers, so your regio and stereochemical control in the synthesis is absolutely paramount. Now, the various ways that organic chemists have used to define stereochemistry in this type of process, the use of polycyclic intermediates is an extremely attractive one, because the inherent locked stereochemistry of a polycyclic compound can be used to define not only the relative chemistry of the 2 carbon-carbon bonds, but also absolute stereochemistry. And then in addition, you can use the effect that one ring might have on the chemistry of the other to define regioselective reactions. And this will be the case in this synthesis. Now, because we want to make a chiral molecule, at this point, we have in fact to resolve our starting material. And the resolution relies on this effect that one ring has on the chemistry of the other. If one just considers this model for a second or two, here you see you have the 4-membered ring, and here the 5-membered ring. And if we view it from the side, then quite clearly the 4-membered ring is differentiating the 2 sides of the 5-membered ring, so that a reagent attacking the 5-membered ring coming in from the back here is going to be very sterically hindered by this 4-membered ring. On the other hand, attack from the other face of the molecule, clearly there is nothing to stop the reagent approaching. If one considers, first of all, the process of resolution, well, in fact, the way we do this is, first of all, to make a bisulfite addition compound, and then, having done that, we make a salt with one of the optical isomers of alpha-methylbenzylamine. Now, normally, of course, to make a bisulfite addition compound of a ketone, you're creating a new asymmetric center. But because the 4-membered ring and the chemistry of the 4-membered ring is governed by the 5-membered ring, our reagent only attacks the 4-membered ring from the top face. It can't get in under here, because this 5-membered ring makes this very steric. So we only get bisulfite addition from the top of the ring, creating our new asymmetric center, as I've shown you, and then formation of the salt.
Since the bicyclic compound exists as a pair of enantiomers, and these can form a salt containing only one isomer of the chiral amine, the salt exists as a pair of diastereoisomers, which can be separated by crystallization. Since formation of the salt and the bisulfite addition compound is reversible, regeneration of the bicyclic ketone from one pure diastereoisomer then leads to our enantiomerically pure synthetic intermediate. Notice that in this bicyclic compound, we've already started to fix the stereochemistry at 2 centers. The other 2 centers are created selectively because the 4-membered ring controls attack at one face of the double bond in the 5-membered ring. So the next reaction employed focuses on the double bond. It's bromohydrin formation. This is a 2-step reaction. First, the electrophilic bromine forms a bromonium ion. Then this is attacked by water from the opposite side to the bromine, leading to overall anti-addition.
Now, the first stage of bromohydrin formation is attack of a bromonium ion to form the positive species. Now, in this way, the bromonium ion can either attack from this face or alternatively from this face. And for the reasons I've already explained, quite clearly, attack from the open face here is the one that is preferred. So the bromine is going to be either on this carbon atom or this carbon, but on this side of the molecule.
Computer graphics can reinforce this point. Attack of the bromine on the face of the double bond opposite the four-membered ring occurs readily. But attack on the other face is hindered by interactions of the bromine with the four-membered ring.
Now the next stage in the process of bromohydrogen formation is attacked by the water nucleophile on the bromonium ion. And the water nucleophile now has to approach the back of the five-membered ring by virtue of the mechanism of the reaction, and it can either approach the back of this carbon atom here, and quite clearly in this situation undergo severe steric interaction with this carbon-carbon bond, or alternatively can approach the back of this carbon atom here, and this of course is clearly because it is now in a 1-3 situation from here to here, whereas here it's in a 1-2 situation. So this is the preferred attack, and that is why we only see one isomer of the bromohydrogen rather than the four theoretical possibilities.
Now we have defined the stereochemistry at the four chiral centres, but let's stop for a moment. Our target molecule is a prostaglandin analogue, and the synthesis is flexible enough to lead to a range of such compounds. So what is the general strategy, and why was this synthetic route chosen as a means of synthesizing a range of prostaglandins?
Well, this really started from an observation that André Dryden had made in the literature some years previously. And he'd observed that if you took the dibromo analogue of our bromohydrogen and treated it with sodium ethoxide, then you formed, in very good yield, and with regio and stereochemical control, which is most important, this ethoxy-substituted bromo-norbornonone. And he thought about the mechanism of this process and surmised that perhaps it occurred via an intermediate of this type. Now, why should one be interested in the formation of norbornonones? Well, if we consider a norbornonone of this type, and we view it from this direction, so this situation here becomes our five-membered ring, then in fact what we have is this. And looking at these groups and looking at the groups on the five-membered ring, let's see how this now relates to our product that we want to make, our prostaglandin. Well, you'll see that what we actually have here at C9 is a carbon-oxygen bond which has the correct stereochemical relationship to become the C9 carbon-oxygen bond in our product. Here at C8 we have a carbon-carbon bond, and this has the correct chemistry and stereochemistry to form this carbon-carbon bond of the prostaglandin acid side chain. Our carbon nucleophile bond here at C12 is correctly placed to form this carbon-carbon bond in our product. So clearly if we use an organometallic nucleophile, then we might be able to put this prostaglandin side chain in. Here at C11 we have a carbon-carbonyl bond, where obviously in the product we require a carbon-oxygen bond, but cyclic ketones undergo biobiligar oxidations, and we would expect to be able to insert oxygen in this position using a biobiligar and thus create this carbon-oxygen bond here.
The idea is that once the stereochemistry of the four chiral centres has been controlled, the norbornonone is formed, and it's at this stage that the reagents can be varied to give the range of prostaglandins and analogues. So how is this carried out in practice?
Well, we found that if we took our bromohydrogen and protected it, you'll see, as a silyl ether, and treated it, and this is most important, with a non-nucleophilic base, in this particular situation, potassium tertiary butoxide, that you could form the enolate anion, and this enolate anion would then undergo an intramolecular alkylation with concomitant loss of the bromine. And this would in fact afford the tricyclic ketone that we required. But this compound now, because there was no nucleophile present, failed to react any further, and we could now isolate it as the tricyclic ketone. Now, of course, the absolute and relative stereochemistry of this new carbon-carbon bond is completely fixed by the fact that we're using a polycyclic intermediate again. Now, the next stage of the process is to take the tricyclic ketone, which can be isolated and stored, and react it with a nucleophile. And it is extremely reactive to nucleophiles. And the nucleophilic attack is a regio-specific one and a stereo-specific one, again controlled, the chemistry totally controlled by the polycyclic nature of the intermediate, with formation of the corresponding norbornone enolate, which then protonate to give us the norbornone product.
Once again, the reaction is regioselective. The nucleophile has attacked a single carbon on the 5-membered ring, opening the 3-membered ring, giving the enolate. But there is another option. In theory, the nucleophile can attack this alternative carbon in the same way, going back to a bicyclic compound containing 4 and 5-membered rings. But this is not observed. Why? Because of the high ring strain, the nucleophile can attack either of these 2 carbons. For a number of reasons, attack of this carbon is preferred. For example, there is a little steric hindrance to this mode of attack, but attack at the alternative carbon is hindered by the bulky Salal protecting group and the rest of the molecule. So the nucleophile preferentially attacks only 1 carbon in the 5-membered ring. For the synthesis of prostaglandins and their analogues, the choice of the nucleophile will dictate the form of the side chain. If you're making a prostaglandin D2, for example, an organocuprate is chosen, giving the lower side chain. Elaboration of the carbonyl then leads to the upper side chain. Exactly the same intermediate is used to create the target molecule. Here the nucleophile is morpholine, and again, elaboration of the carbonyl leads to the side chain. If R is benzyl, the result is the candidate drug. The details of these reactions are given in the broadcast notes, but the main point is by carefully choosing your nucleophile and elaboration of the carbonyl, you can make a wide range of prostaglandins and their analogues, a truly flexible synthesis. This synthesis is also flexible in terms of the laboratory manipulations. The addition of the nucleophile to the tricyclic compound usually requires low temperature and an inert atmosphere, but such conditions are routine in most synthetic laboratories. Indeed, the synthesis is sufficiently flexible to be able to be scaled up to produce large amounts of the required analogue for clinical trials and ultimately commercial sales of the drug. So now, Glaxo are able to make their candidate drug in the quantities needed for trials and evaluation. The synthetic chemistry worked, but nothing is straightforward.
Well, having got 19437, this was not in fact potent enough for us to develop it as a drug. So we had to do some medicinal chemistry around it. We had to make analogues of it, slowly change the molecule piece by piece. And of course here the synthesis and its flexibility was absolutely paramount. Until eventually we found a compound which was numbered NH23848. Unfortunately, fairly early on into the toxicological studies, this molecule showed itself to be teratogenic. In other words, it caused damage to the unborn fetus. Now, if you look at this molecule, you can see that we have a beta-alkoxy ketone. And you would expect, under acid and basic conditions, that this molecule might be chemically degradable to the corresponding alpha-beta unsaturated ketone, and this would be the driving force for this elimination reaction, and you would be generating this alpha-beta unsaturated ketone and biphenylmethanol. And it turned out that biphenylmethanol is a teratogen, and indeed the toxicity of our ANH23848 was due to a chemical breakdown product, biphenylmethanol. Now, if you think about that from a chemical point of view, well, clearly we must substitute the ketone for some alternative group, which will not, in fact, drive this type of elimination process. And it was, in fact, in that way that we evolved ANH32191. And this drug, you'll see, has, and this is quite surprising, the unnatural stereochemistry of the hydroxyl group at this position instead of the carbonyl group. And chemically, this compound is quite stable, and it is our development candidate.
The arachidonic acid cascade is an extremely useful family tree, but we would not have been able to map it without the use of chemical techniques. More importantly, it would be impossible to translate any of this biological understanding into a usable drug without using chemistry, and in particular synthetic chemistry, to probe receptor sites. Chemistry provides a solution to biological problems.
In fact, the majority of companies looking at the arachidonic acid cascade are, I think, very taken by the chemistry. And you will find an enormous amount of beautiful chemistry was done, but I think, in fact, the biology and the biological approach was not a very logical one. So that people tended to make analogues from an analog point of view and test them without really thinking about receptors, receptor classification, and really objectively defining what their targets were. For this reason, it has been, 20 years, I suppose, since the prostaglandins were first synthesized, but to date, no major drugs have yet appeared. Our approach, which was really, because after all, the medicinal chemist is solving a biological problem. We're not solving chemical problems. The whole thing about the drug industry is solving a biological problem, and therefore you should really approach the thing from a biological sense. The biology must lead the chemistry. Now, clearly, in this particular area, one had to have flexible chemistry in order to go into the biology in the first place.